welcome back to The Explainer. You know, AI can do some incredible things, right? Write poetry, generate stunning images, but ask it to solve a really tricky multi-step problem and it just falls apart. So today, we're digging into a fascinating paper that proposes the way to teach AI not just to know the answers, but how to actually think its way to them.
All right, so here's the game plan for today. We're going to start by looking at this reasoning wall that AI keeps hitting. Then we'll unpack why the current methods just seem to get lost. After that, we'll get into the good stuff, the diligent learner and its toolkit. We'll even see how it learns backwards, which is super cool. And finally, we'll ask the big question, is this a genuine path to superintelligence?
Okay, first things first. Let's really frame the core problem here. What is it that's holding AI back from becoming a truly robust problem solver?
I mean, we see AI do these amazing things every single day. But the second a task needs more than one logical step, some real trial and error, the ability to recover from a mistake, that's when even the biggest, most powerful models can just completely faceplant.
And this slide right here, this really gets to the heart of the problem. We tend to train these models on what you see on the left, the ideal path. It's that clean, perfect, step-by-step solution you'd find in a textbook. But real-world problem solving, well, that's what you see on the right. It's messy. It's a maze of possibilities, full of wrong turns and dead ends, just like the paper describes.
And this creates what the paper calls the golden path problem. Think about it. The AI is only ever shown that perfect, polished, final answer. It never gets to see the messy journey it took to get there. So, of course, it never learns those really critical skills, like how to explore on its own, or, importantly, how to recover when it makes a mistake.
All right, so if that's the problem, what have we tried so far to fix it? Let's take a look at the current methods and see exactly why this paper argues they just don't cut it. Okay, so the most common method is something called supervised fine-tuning, or SFT for short. And you can basically think of it as teaching the model to be a world-class mimic. It just learns to perfectly imitate the examples it's shown.
But here's the killer flaw, and the paper calls it distribution drift. The moment that Mimic makes a single wrong move, it steps off that golden path it was trained on. Suddenly, it's in totally uncharted territory. And from that point on, every single step it takes is probably going to be wrong too. The whole chain of reasoning just collapses.
So then you have other approaches, like tree of thoughts. These try to build out a search tree to explore different options. But they run into one of two major problems. Either they try to explore every option at once, what's called a combinatorial explosion, which is just computationally impossible for deep problems. Or they follow one single path all the way to the end, and if they fail, they can only backtrack one measly step. It's like being a blind explorer who has no idea where they came from.
And what about something like reinforcement learning, which is all about trial and error? Well, this is where the math really works against us. Imagine the problem with, say, 10 really tough steps. Even if you have a 50-50 shot at each one, the odds of randomly guessing all 10 steps correctly in a row, it's astronomically small, basically zero. That's the exponential problem you see here. The model almost never stumbles onto the full correct solution, so it never gets that crucial reward signal it needs to actually learn anything.
Okay, so if all these other methods are flawed, what's the solution? This is where the paper introduces its big idea. A brand new algorithm called the diligent learner, and it's designed from the ground up to navigate that messy, complex maze of reasoning we saw earlier. So the diligent learner has this really cool toolkit with three main parts. First, there's the generator, which is like its explorer, always suggesting new paths to try. Second, there's the validator, which is like its compass, checking if each step is actually logical. And third, and this is the really critical part, it has a smart backtracker. This is the eraser that knows how to learn from failure instead of just giving up.
And the whole approach really hinges on this one simple but totally brilliant observation from the paper. Think about it. It is so much easier to check if a math problem solution is correct than it is to solve it yourself from scratch. The diligent learner is built to take full advantage of that fact.
Okay, so let's visualize how this smart backtracking actually works, because this is the absolute game changer. Imagine the model follows a long path of reasoning, from step 0 to 1, all the way to 5, and then hits a dead end. Now, a simple system would just go back to step 4,
but not the diligent learner. It's smart enough to realize that the entire line of reasoning was flawed, maybe because of a mistake it made way back at step 0. So it jumps all the way back to the source of the error and tries a completely different path. This is what makes it so powerful.
So you're probably wondering, how on earth does a model learn to do something that smart? Well, the training strategy is just brilliant, and it's completely counterintuitive.
Instead of trying to learn a problem from the beginning, like we normally would, the diligent learner gets trained backwards, starting from the end. It's a strategy called a reverse curriculum. First, it just learns how to solve the final step. Once it masters that, it learns to solve the last 2 steps, then the last 3, and so on, working its way all the way back until it can solve the entire problem, from start to finish.
So why on earth would you do that? It sounds a little weird, right? But it's actually genius. By starting with a problem that's already almost solved, the model is always facing an easy task where it's very likely to succeed. It's like learning to ride a bike with training wheels that you slowly raise over time. It gradually builds up both the skill and the confidence, so to speak, to eventually tackle the entire complex reasoning chain from a blank slate.
All right, so let's pull back and look at the big picture. What does all of this mean? This is where the paper really goes for it, connecting this robust reasoning framework to some huge ideas about the future of intelligence itself.
So, to sum it up, the diligent learner is basically purpose-built to fix all those critical flaws we talked about earlier. It beats distribution drift because it actually learns how to explore and backtrack from mistakes. Search isn't just an add-on, it's baked right into its DNA. And it manages to do all of this efficiently, neatly sidestepping those insane exponential costs that just cripple the other methods.
And this brings us to the paper's incredible conclusion. The authors put it right out there. They're not just saying this is a way to solve today's problems a little bit better. No, they're arguing that this framework, this is a concrete, plausible path towards building artificial agents that can navigate reasoning trees so deep and wide that they actually exceed our own human cognitive abilities. And that really leaves us with a huge provocative question to chew on. Are we just building more and more sophisticated parrots, systems that just mimic patterns they've seen? Or is this the moment we're finally starting to teach them how to actually think? If you want to dive deeper into more of this kind of groundbreaking research, and you want it broken down just like this, make sure you subscribe to VibeDoc. We'll be back with more explainers soon. Thanks for watching.